Good morning, students. Let us start today's class. In the previous class, I had shown you some practical circuits with examples of negative feedback. Before that, we had done the block level analysis of negative feedback. Later on, we studied some 4 circuits which were having actual feedback concept there. And when you studied emitter follower in the first module, you would not have thought that it is having a feedback also there. But emitter follower also is going to have a feedback, because when the emitter resistor is having the output voltage across it, that itself is causing the reverse biasing of the base emitter junction. That way, in many circuits, even though when the feedback circuit is not present, or the feedback concept itself is not present, there will be an indirect feedback happening in those circuits. That is why we had seen some examples, and today we will continue with my PowerPoint presentation only, because in the last class I showed you the PDF notes. So now continued learning, because learning never stops. We keep on learning lifelong about many things. Technical things, scientific things, spiritual things, healthy things. We keep on learning lifelong. Now, this learning continues after the chalk and talk. Whatever I showed earlier with the PDF notes, that I used to do it using board and chalk piece only, because we used to write all those derivations on the board. Now in the online mode, I showed you the notes and I just explained all that. Let me continue with the presentation now. Today we will see the last point in the negative feedback concept, that is called phase and frequency considerations. You are already familiar with the frequency response of the amplifier, where you have seen there is a dip in the gain at the lower frequency side, and there is a dip in the gain at the higher frequency side. There is a maximum gain only at the mid band. You are already familiar with that particular frequency response, which we had discussed in detail in the third module itself. But till now we did not bother much about the phase response. Let me just try to write one diagram here. Now the first point says the gain of an amplifier is stable only at the mid band. There is a typo mistake here. Later I will change it. It is not mid band, it is mid band. By mistake N has come there. Now the gain drops off at low and high frequency ranges. This we are already familiar. That means, let me write a small diagram here. Let me choose a different color. Now we know the response is like this, and x-axis is frequency, y-axis is gain. Let us indicate it as voltage gain itself. We will typically take the example of the voltage series feedback amplifier itself. So now we have seen we have one point FL here, or low frequency cutoff, and then we have one more point FH here, high frequency cutoff. And now we generally think that this is the maximum gain. This portion where the mid band, there is the maximum gain. So we have been discussing only about the gain response with the increase in frequency, whereas we assumed always that there is a 180-degree phase shift in case of a common emitter amplifier. That is what we thought, and we thought that in all the frequencies there will be this 180-degree phase shift. Let us say this is an amplifier symbol. This is an amplifier symbol. And we thought if the signal is like this at the input, at the output the signal will be like this. And that is how we assume that for all frequencies the phase shift is 180 degree. But now let us discuss a little bit about the phase response as well along with the frequency response. Now the discussion today is that the phase will not be 180 degree at all times. Again, the phase will also be exactly 180 degree only in the mid band. Otherwise, even at the lower frequency or at the higher frequency, phase shift can also change. Why? Can anybody tell me why phase response also will change? Till now we have been discussing only the frequency response. Now I am telling you that even the phase response will not be ideally 180 degree. Even the phase response will change. Can anybody tell me why? Of course, students are thinking that I only should tell because I am only teaching, right? Now, why frequency response changed at the low frequency and high frequency ranges? At the low frequency ranges, it was the capacitances which were external to the circuitry which influenced the frequency response. And at the high frequencies, it was the internal parasitic capacitances which affected the frequency response. This we had seen in the third module itself. That means that the circuit is not ideal at any point of time. The circuit will not be ideal. As such, nothing is ideal in this materialistic universe. Wherever there is material, there is always non-ideality. So, circuits are made up of again materials only. Semiconductor materials or conductive materials or insulative materials. And all these materials have non-idealities. So, because of the non-idealities only, we had non-ideal frequency response. Now, for the same reason, we will have non-ideal phase response. You might have already studied these things in the course called network analysis. I keep on referring to some other courses because many basics are taught in many other courses with the different context altogether. Finally, all these are related to each other. So, it is not possible to teach everything in one particular course as such. That is why the complete curriculum for engineering contains many courses distributed among the 4 years. So, in the course called network analysis, you might have already studied about the angular differences that occur when the signal passes through a LC network or through a RC network or through a combination of RLC networks, where you always use the formula of calculus to arrive at the difference in angles. The circuits that are leading and the circuits that are lagging with respect to the input signal. So there, what does it mean? When you actually are computing the phase response there. You had an amplitude response there, you had a phase response there. Whereas in AEC, we focused more on frequency response. Now, you recall all those phase responses which you studied in the course called network analysis. Then you will understand that even the phase will not remain same throughout the frequency band of consideration. That means, even though we generally say that 180 degree is the phase shift between output and input in case of a common emitter amplifier, it will be an ideal case again in the mid band. At the other bands, even the phase is going to have its own non-ideal responses. So that is the discussion here now. Of course, it is a brief discussion. I will not go into much more detail here. So let me continue now. Just a minute. Let me at least correct this typo error. Then I will share it once again. Okay, now I have corrected that error. The gain of an amplifier is stable only at the mid band. The gain drops off at a low and high frequency ranges. This we have seen. Ideally, phase difference between Vs and Vf has to be 180 degree at all frequencies. But as I told you, this is true in the mid band, but it is not true in the other bands. But at the two ends, if there is additional phase shift, then Vf may become in phase with Vs, leading to instability. Please understand this. Let me annotate once again. I will write a small diagram here. Now what we expect is when the input is like this, we want ideally the output to be like this. So this is only at the mid band where there will be 180 degree phase shift. Now at the other two ends, maybe at the lower frequency side and the higher frequency side, if there is additional phase shift because of the circuit's non-idealities, then the feedback voltage may become in phase with the input voltage. What happens if the feedback voltage becomes in phase with the input voltage? Till now we have been discussing negative feedback, where we wanted to have the 6 advantages out of the negative feedback. Even the one disadvantage was the reduction in gain, we had the 6 advantages. Now at any particular high frequency band or the low frequency band, if at all the feedback voltage becomes in phase with the input voltage, then what happens is, instead of having a 180 degree phase shift, what is going to happen there? The feedback voltage will be getting added to the input voltage. Till now we have seen that the feedback voltage will be getting subtracted from the input voltage. But because of this additional phase shift, now the feedback voltage, if it becomes in phase with the input voltage, then the circuit will start oscillating. In the sense, gain will keep on increasing because Vf and Vs will be in phase. Please recall, Vs and Vf are out of phase. Actually, Vi is Vs minus Vf. That is how we had discussed earlier. But if Vf and Vs are in phase, then the input voltage will become Vs plus Vf. When it becomes Vs plus Vf, now that keeps on getting amplified by the amplifier, and the same voltage is fed back through the feedback network. Now the circuit will unnecessarily have increased gain, that is called as instability. Till now we thought that the circuit will be highly stable and there will be normal control of the gain with the negative feedback. But it is not the case with the higher band. When the frequency increases, the circuit may become unstable, or circuit will become unstable. Now based on this, one scientist called Nyquist worked more on the stability factor of a particular amplifier circuit. We are going to discuss that in the next slide now. Thus the amplifier may start oscillating at some frequency where it is supposed to be stable at all frequencies. Look at this point. When the feedback signal and the input signal, when they are in phase, there will be unnecessary increase in the amplitude of the input voltage. When there is an increase in the amplitude of the input voltage, that is going to be amplified by the amplifier itself. Let me make it clear once again by writing the feedback network here. I will quickly write the feedback network here. See, we had A here and we had beta here. Right, we had A here and we had beta here. And this was the input signal. This was the output signal. The portion of the output signal was coming back to the input signal. So it used to be like this again. you can see this is Vs now and this is Vf now. Now Vf is out of phase with Vs. That is why Vi was Vs minus Vf. So the gain was reduced and we had the A Vf is A by 1 plus A beta. That was the equation which we had derived. Now imagine that because of some non-idealities, here the phase shift may not be 180 degree. Imagine at some high frequency, now the signal remains same like this. Imagine this way, at some high frequency, because of the non-ideality, phase shift will not happen in that amplifier exactly at 180 degree. Imagine that this input and the output are in phase at a particular high frequency. Then what happens here? At the feedback network, what happens? At the feedback network now, the signal will be in phase. Now when the signal is in phase, the feedback voltage is in phase with the input voltage. Now this will get added up now. Instead of becoming Vs minus Vf, it is becoming Vs plus Vf now. Now this will increase. And then this will further increase. It will keep on increasing. When it keeps on increasing, after some time, gain may become infinite because of this loop now. Now this becomes a positive feedback. Why? Because the feedback signal is in phase with the input signal. Now it is resulting in a positive feedback. There will be a continuous increase in the gain one after the other by a factor of this A. And after some time, even if this is removed, even if this Vs is removed, it will keep on producing this particular wave, because this Vf is coming back and it would have become so large because of the continuous amplification. Vf would have become so large that itself will keep on looping here. Now that is called oscillation, that is instability of the amplifier. You would have observed in many public functions, when the amplifier's gain is slightly kept at a maximum value, whenever somebody is speaking with the microphone in the hand, you would have suddenly observed an increase in the sound, a squealing sound or a very high frequency sound that is coming up. So at that time, somebody has to go there and reduce the gain of the amplifier. Then it will become normal. This you would have observed in many public functions in the olden days, or maybe recently also. Nowadays, all the amplifiers are also controlled by means of a DSP architecture. So many times the amplifier itself may be controlled by a microcontroller or a microprocessor, if it is digitally controlled. Otherwise, even now, whenever we have such audio systems, as soon as it is switched on, we will see a high frequency sound for a few moments. Later on, somebody has to reduce the gain of the amplifier. Why is it happening? It is happening because if the gain of the amplifier is large, that frequency comes back and even the atmospheric noise is going to be amplified by the microphone. Actually, microphone picks up the atmospheric noise also. That noise goes to the amplifier and that is coming out from the speaker. Whatever is the sound coming out from the speaker, that goes back to the microphone, and that is how the looping is happening. That results in a positive feedback. When that results in a positive feedback, if the gain is not controlled properly, circuit will start oscillating. Now in our regular case, this is not supposed to happen. That means the amplifier is not supposed to oscillate at any frequency. But it will happen now because of the non-ideal phase response. So now, what is the next measure for us now? Hence, the value of loop gain was investigated by Nyquist. Loop gain means the gain along with the feedback. That was investigated by Nyquist so as to obtain a condition for the stability of the amplifier. We want our amplifier to be stable at all frequencies. So, Nyquist did a lot of work on that and he obtained a condition for the stability of the amplifier. With AF equals A by 1 plus A beta, you can see this equation, which is a magical term now for us. We are very familiar with this particular term. The gain with feedback is nothing but A by 1 plus A beta. Now when A beta is equal to minus 1, what is going to happen? When A beta is going to be minus 1, it is going to become 1 minus 1 at the denominator. So A by 0. That means AF is going to be infinity. Now you can look at this. Till now we have been thinking about A beta as a contributor to the amplifier. Now due to any reason, if A and beta when their product is going to be minus 1, then AF is going to be infinity. Always we thought that AF will be less than A. But in such conditions where A beta is going to be minus 1, AF will be infinity. Why A beta will be minus 1? That we will see later on. First you understand the term A beta is going to play a major role now. That means the gain of the amplifier and the percent of the output taken back to the input by the feedback network, that product, if it is going to be minus 1, then AF is going to be infinity, or the feedback gain which was supposed to be lesser, now it is becoming infinity. Now this indicates instability, which means what? Maybe without the input signal also, circuit will produce signals unnecessarily. We wanted the input signal to be amplified at the output. Instead, without the input signal itself or without the desired input signal itself, the circuit will produce some output signal which is unwanted. So this is called instability. Hence, the Nyquist diagram is utilized to plot the gain and phase shift as a function of frequency on a complex plane. See, Nyquist plotted two curves now. One is a gain curve and one a phase curve. Till now we have been interested only in the gain curve. Nyquist worked on the phase curve so as to have an idea about the stability of the amplifier. So this is as a function of frequency, gain as a function of frequency and phase shift as a function of frequency on a complex plane. On a complex plane in the sense, you are already familiar with this. X-axis is the real plane, real axis, and y-axis is the imaginary axis. In other words, whenever any such response is represented by means of a complex number, you will always have alpha plus j beta as the complex number, right? Or a plus ib is a complex number, or x plus iy is a complex number, where x is the real part and y is the imaginary part. By the way, I had asked you a question many classes before. Why this I is utilized in all our analysis? Even though I is square root of minus 1, why is it utilized in our mathematical analysis? If anybody has found out the answer, you can tell it to me in this class, either by unmuting yourself or by putting it in the chat box. If nobody has found out, then later on, if somebody asks me, then only I am going to tell the answer. Not in today's class. I want you people only to explore why we are using that square root of minus 1 in our mathematical analysis, even though it is not existing. Square root of minus 1 does not exist at all. Why we are using it? Because we are using it, we are calling it as imaginary axis and real axis. Then we call it as a complex plane. Complex plane in the sense, instead of the regular xy axis with 4 quadrants, we will have the quadrants with real and imaginary values. But if the values are imaginary, why are we using them? Because we are using square root of minus 1. Why we are using square root of minus 1? That is the question. Now using the imaginary value, we are going to arrive at some decisions also. Now, why is that necessary? Was my question earlier. If any of you have found out, you can tell me the answer now. Okay, it seems nobody has found out. Okay, you take your own time, you find out on your own, and you can tell me the answer. Now Nyquist diagram is a plot of gain curve as well as phase curve with respect to frequency on a complex plane. Let us see that curve in the next slide. Now this is that particular curve. You can see the x-axis is the real axis and y-axis is the imaginary axis. Now this is a complex plane. Even though it is not indicated, you will have to visualize it this way here. Now we have a complex number for the response of the circuit elements. Now the Nyquist diagram combines the two Bode plots of the transfer function. Which are the two Bode plots? The two Bode plots are the gain plot as well as the phase plot. I will show those plots later on. But this Nyquist diagram is a combination of both of them. Here you can see a circle is there. But you can see the circle in the left hand side when it is going down this way, it is coming back there. Frequency is in the increasing order. It is shown here initially f equals 0. Now gradually f is tending towards infinity. Please remember this is a complex plane. So in the complex plane initially we start with f equals 0, then f1, f2, f3, f4 like that. It goes on f5. It is in the increasing order as f is tending towards infinity. You can see it here. Frequency is going towards infinity, increasing. When it is increasing, you can see that in the complex plane there is an angle and there is a blue line. What is this angle? The angle is the phase shift. When the frequency is increasing, there is going to be a phase shift. Now, gradually when the frequency is coming up to f5, we can say the phase shift is 180 degree. And later on, the phase shift is further increasing. That is what the circle indicates. This is a great work done by Nyquist many decades before. So with the increase in frequency, the phase is also not going to become fixed. The phase is also going to change. That is what this angle indicates. See, we have this line. You will have to visualize this blue line which is moving all the way here. When the blue line moves towards f5, that is when we say the phase shift is exactly 180 degree. That is why it is always in the left half of the complex plane. Now when the frequency increases, now the phase shift also does not remain 180 degree. You can see that. Phase shift is further increasing. And at one point of time, phase shift will become 0. The phase shift was 0 initially when frequency was 0. Because for DC values, there is no phase shift at all. But when we applied the input signal F1 till F5, phase shift kept on increasing and it went on going up to 180 degree. You can see this line here, no? This way it went on up to 180 degree. Now if this line goes upside, what does it mean? The phase shift is increasing further beyond 180 degree. And when the frequency is increasing order, at some point, phase shift will again become 0. So even at the lower frequency side, even at the higher frequency side, phase shift is not 180 degree at all. That is what is indicated by this symbol phi. Okay, this is that phase angle. Now what is this A beta? A beta is the gain factor, right? We already have this particular terminology, A by 1 plus A beta. A into beta. A is the gain of the amplifier. Beta is the fractional part of the output taken out at the feedback circuit. Now A into beta is a factor here now, and Nyquist had indicated in that formula that when A beta equals -1, then we have infinity feedback gain. Now you can see here this A beta. Now A beta is gradually increasing. When it reaches to F5, phase shift is 180 degree and A beta is reaching a particular value. You can see that in this circle, A beta will have a maximum value when the frequency reaches F5. Otherwise, A beta is also going to get reduced here. Let me annotate. See, if at all I have to write this A beta line, which is corresponding to F3. I can write it this way. Now the length of A beta at F3 is less than that at F4. Now when this will have maximum value? Only when A beta is having the maximum value, only when the frequency is reaching F5. Further, Again you can see, no, I am unable to write a straight line. Let me write it here, only leave it. You can see that A beta is going to have a reduction in its magnitude when the frequency increases beyond F5 also. Now that is what is indicated by this Nyquist diagram, which is written in the complex plane. Now don't get confused by the frequency response curve of Bode. In the Bode plot at the mid frequency, we have stable gain and stable phase shift also. But Nyquist indicates in a complex plane that with the increase in frequency, magnitude also will change and phase also will change. Now based on this, what is the conclusion? As A beta as a complex number contains both gain and phase information, A beta is a complex number. It is of the form of x plus iy. So it contains, x contains the amplitude information and y contains the phase information. I hope you have to recall all these things. You have already studied the complex algebra in the mathematics also, and you have studied its application in network analysis. So A beta as a complex number contains both gain and phase information. And the Nyquist plot indicates that the gain is 0 at 0 frequency and the gain as well as phase increase with increase in frequency. This gain as well as phase increase with increase in frequency. At a particular frequency, gain is maximum. That is, at point F5, the gain is maximum. And phase shift is 180 degree. You can see it here, no? Phase shift is 180 degree. It is at the left side of the complex plane. It is minus 180 degree. So, gain is maximum and phase shift is 180 degree, after which the gain decreases back to 0 and phase shift also becomes 0. You can see this A beta also comes back to 0 and phase shift also comes back to 0. Which means when the frequency is increased, gain also may not remain constant and phase also will not remain some angle. Phase also will come back to 0. That is the indication from this Nyquist diagram. Now let us relate this particular diagram to the Bode plot. Bode plot is x-axis frequency and y-axis is gain, or x-axis is frequency and y-axis is phase. We can have a gain plot, we can have a phase plot. Those are the two Bode plots. Now Nyquist has combined both of them in this particular diagram. Now based on this diagram, Nyquist will later give a condition for stability as well. That is quite interesting. We will see that now. Based on the, I am unable to see the upper point here. Okay, now I am able to see. Based on the value of A beta, the Nyquist criterion of stability can be stated as the amplifier is unstable if the Nyquist curve encloses the -1 point and it is stable otherwise. Let me show you the picture. The amplifier is unstable if the Nyquist curve encloses the -1 point and it is stable otherwise. See, amplifier is unstable if this -1 point comes inside the response of the amplifier. Anyway, Nyquist has indicated that with increase in frequency, phase is also going to change, gain is also going to change, it is come back to 0. That is fine. But still then, amplifier will be stable. Amplifier will not become an oscillator, provided at the left side that -1 point is there. No, that -1 point should not be inside the Nyquist diagram. Then the amplifier is stable. If it is inside the Nyquist diagram, then the amplifier is unstable. This is the great invention of Nyquist. That is where he indicated about the value of A beta. If A beta becomes -1, then we know, right, that A by 1 plus A beta. If A beta becomes -1, A by 1 minus 1 is going to be AF equals infinity. That should not happen. So let -1 be outside the Nyquist plot for a given amplifier. That minus 1 should not be inside the Nyquist plot for the given amplifier. Now, if the minus 1 is inside the Nyquist plot for a given amplifier, then the amplifier is definitely unstable. That is going to work like an oscillator at some particular frequencies. This is called Nyquist criterion for stability. So, I will repeat it once again. The amplifier is unstable if the Nyquist curve encloses the minus 1 point, and it is stable otherwise. I hope you have understood this. This diagram indicates that minus 1 has to be outside the Nyquist plot for the given amplifier. It should not be inside. Based on this, we have something called gain and phase margins. The feedback amplifier is stable if A beta is less than 1 when phi equals 180 degree in the feedback circuit. That we have seen now. A beta should not be equal to minus 1 at that time. So, A beta should be less than 1 when phi is equal to 180 degree. However, the amplifier with A beta equals 0.7 will be more stable than the one with A beta equals 0.9, both measured at 180 degree. What does it mean? If A beta product is lesser, then the amplifier is better. If A beta is more, then the amplifier is somewhat less better. But A beta should never become 1. Why? That A is having a phase shift. So, A is basically negative sign. So, negative sign, A is minus now into beta, that is going to be minus 1. If A beta is going to be minus 1, then the circuit is going to oscillate. So, A beta, if it is nearer to 1, then again we are nearer to instability. If A beta is 0.7, then that particular circuit is more stable. If A beta is 0.9, at that time also the circuit is stable, but it is very much nearer to instability. That is the idea here. Now, based on that, we have something called gain margin and phase margin. Why? We have this phi equals 180 degree also we have, and A beta also we have. So, based on this, we have two concepts called gain margin and phase margin. Gain margin is the negative of the value of modulus of A beta in decibels at the frequency at which phi equals 180 degree. In the next slide, I am going to show you the diagrams. Look at this. The gain margin is the negative of the value of A beta. We already know A beta should not be equal to minus 1. So, modulus of A beta, then put a minus sign, that is the gain margin at the frequency at which the phase shift is 180 degree. Now, what is phase margin? Phase margin is the angle of 180 degree minus the magnitude of the angle at which the value of A beta is unity. See, it is the angle of 180 degree minus the magnitude of angle at which the value of A beta is unity. Now, we have two things. A beta should not be minus 1 when phi equals 180 degree. That means, maybe A beta is less than 1 when phi equals 180 degree. And later on, A beta may become still less than 1 or more than 1, and at that time, the phase shift also would have changed. So, there are two distinct things here now. Phase margin is the angle of 180 degree minus the magnitude of angle at which the value of A beta is unity. If you don't understand it right now, don't worry. In the next slide, it will be more clear to you. Now, you can see this. The upper curve where the gain is coming down. We can assume a DC coupled amplifier here. We will not worry about the lower frequency side at all. We will only worry about the higher frequency side. So, see this A beta. A beta is now coming down. A beta was at a point value here, it is coming down. And wherever the gain is 0, what does it mean? 0 dB. When the gain is 0 dB, it means that output is equal to input. You know that 20 log of V0 by Vi. When V0 by Vi is unity, then the gain is 0 decibels. So, 0 dB gain and minus 180 degree phase makes the feedback amplifier unstable. They should not happen together. 0 dB gain corresponds to unity gain, and minus 180 degree corresponds to the phase shift. They should not happen together. Means A beta should never become minus 1. That is the idea here. The value of A beta should not be 1 as phase shift is minus there. A is minus A. So A beta will become minus 1. A beta becoming 1 and 180 degree phase shift happening together should not happen. That is the idea. If they happen together, then there is no gain margin, there is no phase margin at all. If these two occur at the same frequency, then there is no margin at all. No gain margin, no phase margin. Now you can see here, the gain has come down to unity and the gain is going down further. That means after a certain frequency, the value of A beta is going to go further down only, right? You already know the frequency response curve. Now it is going down below 1. It may become 0.9, 0.8, 0.7, 0.6 that way. Now you can see at a point where the phase angle is 180 degree. You can see in the lower Bode plot, when the phase angle is minus 180 degree, gain is not unity. And when the gain is unity, the phase angle is not minus 180. It is still lesser. That way in this circuit, we have a gain margin, we have a phase margin. It is indicated here, you can see. There is a gain margin because at 180 degree, gain has gone less than 1. It is not minus 1 now. That way we are safe. That means the amplifier is having a gain margin. Similarly, the amplifier is having a phase margin. Why? When the gain is unity, phase has not become minus 180 degree. So that way we have phase margin, which indicates that gain curve and phase curve should not have the same crossover point in the x-axis. That is the idea here. See, the intersection of this gain curve and the phase curve with the x-axis should not happen at the same frequency. If that is the case, if that happens, then there is no gain margin and phase margin for the amplifier at all. Lastly, greater the value of the gain margin and phase margin, greater will be the stability of the amplifier. Means these two crossovers, let me annotate. See, we have this crossover and we have this crossover. These two crossovers are right now happening at different places. They should be like that. If they are happening at the same place, then there is no gain margin, there is no phase margin. The stability of the amplifier at higher frequencies is completely questionable. We cannot rely on that particular amplifier. Now in this case, when the gain margin is larger, when the phase margin is larger, that means there are bigger gaps. When there are bigger gaps in the Bode plot, then it means that the amplifier is much more stable and we can rely on this particular amplifier even at higher frequencies. That is the idea. At higher frequencies, we may not get good gain also, but we can ensure that at higher frequencies, the amplifier will not oscillate at all. Amplifier may not produce good gain, it may not produce good phase margin, phase shift at the higher frequencies, but that doesn't matter. At least the amplifier is not becoming a harmful amplifier. Means amplifier is not going to produce harmful sounds there. Otherwise, the amplifier itself is going to produce a sound, means input sound will not be amplified at all at the output. So that way we can say the amplifier is at least harmless at higher frequencies. But if there is no gain margin, if there is no phase margin for a given amplifier, let us say this is going to happen at the same point. In this curve, it is not happening at the same point. But if it all happens at the same point, let us say it is happening here, or if it is happening here, then the circuit is not having gain margin, it is not having phase margin. We cannot rely on that amplifier because at higher frequencies, it will become an oscillator. That is the idea. Now with this slide, for today, I will close the class, because I have completed one particular point on Yeah, you can see this picture here now. I will not hurry up. For the next class, I will slightly repeat this once again before going for the positive feedback circuits. But you can see in this particular picture that this is the gain curve in decibels, this is the phase curve in degrees, and you can see whenever the gain crossover is happening in the x-axis, phase crossover is not happening. So then we have a phase margin. And whenever the phase crossover is happening, then the gain crossover already crossed. It has come below 1. Down we have this gain margin. So larger the gain margin, larger the phase margin, better is the amplifier. Now based on that, I have the last slide where GM and PM in the Nyquist plot is defined. In the Nyquist diagram, you have a gain margin and a phase margin. Here you can see gain difference before instability, that you can see because -1 point is here. So within that -1 point, amplifier is stable. Similarly, phase difference also you can see, phase difference before instability. So gain margin is defined as 1 over mod of A beta at phase crossover, frequency of phase crossover. And phase margin is defined as 180 degree plus angle of A beta at gain crossover, or the frequency of gain crossover.